All right, everyone, welcome back. So right now we're going to talk about variation of parameters, which is probably the most important, I hesitate to say that. It's one of the most important things that is taught in 309. And essentially, what it is it is a way of solving initial boundary value problems. Or actually, I guess specifically, it's just a way of solving boundary value problems of partial differential equations. So right now, we're going to go over an example of doing this technique called variation of parameters. I want to preface it by saying this stuff is really, really hard. I took this class obviously before. And just now today, I spent a good 30 minutes going through just reviewing, trying to piece together. I even had a problem worked out that I found from when I was doing this for my class. And it's still, even reading through that, trying to do it again, it's really difficult. So if you struggle with this, that's good. That means you're right where you should be. So the way I thought about approaching this problem is I'm going to do an example of a boundary value problem of the Laplace rectangle. What does that mean? We'll go over that in a moment here. It's listed later on in the cheat sheet that I made. So if you want to see the general form written out kind of nicely, I did it in LaTeX, so it looks all nice. You can see that the technique here can be applied to any partial differential equation, and you would do something similar here. Basically, what it allows us to do is it allows us to take a complicated partial differential equation and then turn it into a couple second order, just normal ODEs. And that makes it obviously quite a bit easier to solve. But again, still very, very difficult. So I guess we might as well just jump right into it and you'll see what I mean. But this technique, I'm doing it for a specific problem type. You could do this for other problem types using a similar method. And I hope you see how it generalizes, but we don't have time to get into like a super general form because it gets kind of confusing. So I'm just gonna jump right into it. So I said we were gonna do a Laplace rectangle, and I meant it. So this is the equation, or the partial differential equation for a Laplace rectangle boundary value problem. So what this means is the second derivative. So actually, I guess it's probably worth mentioning. So u here is a function of x and y. So u is some multivariable function that we're considering above like the xy plane. So when I say, this notation, this means the second derivative with respect to x, and you can imagine with the y's it means the same thing, but with respect to y. So we're going to let x go between 0 and some value a, and we're going to let y go between, I'll write that better, y go between 0 and some value b. Okay, great. So this gives us kind of this is sort of the framework that we're going to fit everything into here. So the next piece of information that's important is we want this to equal 0, this to equal this to equal some function g of x. So basically what we're doing here is we're saying we're letting x vary, but we're fixing y at the endpoint. See, we're fixing it at 0 and we're fixing it at b. And we're giving some criteria. We're saying when y is 0, we know that this whole function is equal to 0. When y is equal to b, the whole function is equal to some function g of x. And I hope you see, since we're fixing y, we plug b everywhere and we have a y. So everything that's left is x's, so we're actually we have a single variable function. And then the next one is a little simpler. We're going to go 0, y. So now we're fixing x, and we're saying that both of those boundaries, so again, a and 0, remember a and 0, those are our boundaries. Both of these are equal to 0. Now, I know what you're saying. Wait, Jake, there's 4 boundaries here, which makes sense. It's a rectangle, right? We've got a quadrilateral going on. Only one of them has a function on it. That is a very astute observation. So in practice, you can do this where there's a function where every single boundary is a function. And I'll have a further video explaining kind of what that geometrically means. But as you will see, doing it for one boundary, or basically where everything is 0 but one boundary has a function on it, or representing it, I suppose, is difficult enough. The way that you do it, if you have more than one function, is you solve these problems where, you know, one of your boundaries is a function and then the other one is a function, and then you add them together. So if you had all 4, you will have to do what we're about to do 4 times. Now, there are some simple formulas, and what you can do is you can derive formulas that will kind of work every time, but you have to run through each one of them once. So anyway, I'm getting a little ahead of myself here. Let's just move forward with this problem. So like I said that u is a function of x, y. So this is the crucial thing in variation of parameters. As you probably have caught on to at this point, a big part of differential equations is making guesses. So basically what variation of parameters says is a problem like this, it is safe to assume, for lots of reasons that we don't need to get into, that this function will be some function of x times some function of y, or I'm sorry, times some function of y. Normally we write these as kind of big X of x and big Y of y, just because what we want to do is drop the arguments, but we want to keep track of which part of our differential equation we're talking about. So what this means is we can take derivatives of this. So remember, so u double sub x, or sub double x, I don't know, whatever makes more sense, is the second derivative of this with respect to x. Now, it's again important, we're taking partial derivatives. So that means we treat y as a constant, and we take the derivative with respect to x. So you might be, this is different than implicit differentiation. So what that means is our second derivative with respect to x, it's a lot easier actually. We treat this function y, sorry, I wrote a big y in there. We treat this function y as a constant, which means we don't have to do product rule. It's just our normal derivative rules. Okay, there's no chain rule going on here, nothing strange. So you can probably guess where this is going. So u sub double y is just x of x. We treat that as a constant, and then we take the second derivative with respect to y. Okay. So remember, u sub double x plus u sub double y equals 0. So great. Let's do it. Oops, sorry. Awesome. So this is just applying our first condition, right? This is just adding this and setting it equal to 0. Okay. Now, if we do, oh, I added a plus here. I'm sorry. For the astute among you, may have caught on to that. So basically, the next strategy is we're gonna write this equation like this. Now, I'm gonna be skipping a few algebra steps in the interest of time. Feel free to pause the video and think about what I'm doing here. But I hope everyone will agree that this is equivalent to what I wrote above, right? All I did was subtract off the second term, and then I did a cross multiply, basically, or a cross divide, I guess. A reverse cross multiply, maybe. Okay, so this is the next crucial thing we do in variation of parameters. So the first one, remember, was assuming that we can write this, we can decompose this x, y as some function of x times some function of y. The next thing we do is, it's not quite an assumption, but we just say, okay, well, this is kind of confusing. So we're just gonna go ahead and we're gonna call this sigma. Okay, I don't want to write this every time. We're just gonna call it sigma. Now, what that allows us to do is this gives us 2 equations, 2 second-order single variable differential equations, which is great because that is something that we are used to solving. I'm also going to drop the arguments at this point, and I'll show you what I mean by that. So I've dropped the arguments. I'm not writing x of x anymore, and that's just for simplicity's sake. This is a sigma. I'm going to rewrite that. Okay. So all I did is I took this and I set it equal to sigma, and then I multiplied and subtracted. You see that? You can kind of see if you add this over and divide by x, you get one of these expressions here. And then the other one is, of course, it's kind of analogous, but we've got this negative sign here. So it's like it's going to be a plus sigma. Okay, great. So I'm going to let 307 do a little bit of the heavy lifting here, and we're gonna say that we know how to solve these. These are second order differential equations. We solved this very similar to the way we did linear systems earlier, but it's actually even a little bit simpler. We just use kind of our assumption that these are going to take the form e to the something x because they're some constant times times our original function is defining our second order or our second derivative. So what that means is we can write a characteristic polynomial. So I'm going to do it with r so we don't get confused with the whole lambda thing going on that we had earlier. We get something that looks like this and something that looks like this, plus sigma equals 0, which gives us that, of course, r squared equals sigma. And this r squared, maybe we should write r sub x or something, r sub y, just so we don't get mixed up, is equal to negative sigma. So I would argue this is kind of the third major thing about variation of parameters that we're about to run into. So sigma could be three things, right? Sigma could that's an x, not a sigma. Sigma could equal 0. Okay, sigma could equal 0. Sigma could be greater than 0. Or you probably caught on by this point, but sigma could also be less than 0. Okay. Now this is the case we're going to focus on right now. Now here you're asking, Jake, why are we going to do this? Well, there is the best reason I can give you is that the other two don't work. They give us basically what we end up finding. And I would encourage you to do this as an exercise. For example, let sigma equal 0, and run through this process that I'm about to do with the assumption that sigma equals 0 or is greater than 0. And what you find out is that basically the only functions that could satisfy that are trivial. What do I mean by trivial? Well, we're going to get some constants, and I'll point this out again when we get there, but we're going to get some constants. I mean, you can probably figure this out. We're going to get some constants multiplied times some exponential functions, blah, 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 plus, yeah, right? Because we're doing these second order ODEs. What I mean by trivial is that we discover that the only way that our boundary conditions can be met is if both of these constants are 0, which is not good, right? Because it's fine, but it's not very interesting, right? It means, oh, okay, so if we've got a flat sheet that doesn't do anything, then okay, great, we've satisfied our differential equation. But that's not really why we're here. We're here to find a more interesting solution. So we're gonna just for now assume that sigma is less than 0. We're gonna run with that. Now this is where things get a little confusing, right? So sigma is negative, right? That's what I mean by less than 0. So what that means is that if we take this one step further and we say r sub x equals root sigma, because sigma is negative, this will be complex. You see that? And then, similarly, since we've got a negative sign, this is negative, so that number is going to be positive. So this is going to feel like a little bit weird in notation, but just roll with it. We know that root sigma, this is going to be real. Now, why did I not write a negative sign inside? Well, I didn't write a negative sign inside because, frankly, I don't have a great reason. The reason that I'm not doing it is just because I think it makes things confusing. And it turns out that if you leave it off, you still get the answer you're expecting. But yeah, but the important thing here is that if we make this assumption that sigma is less than 0, we get complex roots of our characteristic polynomial here and real roots on the bottom. Okay. Now, why is that useful? Well, remember, we're trying to solve these second order ordinary differential equations, right? So what's nice about that is knowing that we have complex roots, we can use, again, we're going to let 307 do a little bit of heavy lifting, but that means that we know that the general solution for x, I put the argument back in just to be clear, is going to take this form. Now I'm going to make a clarification in one moment here. So if you're noticing something funny going on here, that's good. I'm glad you noticed. So you might be asking, wait, you told me root sigma was complex. So what you've done is you've put a complex number in here, and so now we've got i's sitting around. Now that is a great observation. And what I'm arguing is that we're going to use the strategy where this will be complex, but it won't have a real part because sigma is like just a constant. It would just be like you might get -5 or let's do -9, which means that you'll get plus or minus 3i. So there's no real part here. It's just imaginary. And so what we're doing here when I say root sigma from this point onward, I mean when I'm talking about this case, what I mean is the coefficient of the imaginary part of the complex number. So actually, when we write this, there's no i's in it. But if that seemed weird, then that's a great observation, because I think the notation is a little unclear here. But we're gonna roll with it anyway, because like I said, this is some hard stuff. So we know this. I'm gonna move this over. So we know one other thing. We know the form that y is going to take. So these are real valued roots. So we know we're going to get exponential functions, right? Now again, remember since we're taking a square root of a real number, we've got a plus or minus sitting out in front. So those are kind of the two options we get. We get sigma y and negative sigma y. So those are kind of our two roots of the characteristic polynomial that we're using here. I'm sorry I didn't write that earlier. That was silly. But now we've got these nice two equations. Now remember, we assumed that u of xy is equal to the product of these two. So if you like, you could write the product just as is. The problem is we don't know what this sigma is, and that's very important. So what we're going to do is we're going to try and use these boundary conditions, because remember, we still have these 4 pieces of information we haven't used yet. We're going to try and use those boundary conditions, apply it to the 2 equations that we have down below, and see if we can find out what sigma is. Then we're going to use that to find out what the coefficients are, and we're going to get a very interesting result. So here is what we're going to do. So the first thing, let's look at the x first. I think the x is going to give us some good stuff. So x of 0, let's think about what that is going to look like. So x of 0 is going to be, let's just plug it in. So c1, cosine of 0, I believe, is 1. So remember, we get 0 times root sigma, which is something, but the point is it's going to be 0. So I believe cosine of 0 is 1, plus sine of 0 is 0. So plus 0. Now, why is this interesting? Well, we know that if we look at these boundary conditions here, u of 0 comma y means we're plugging in 0 everywhere we have an x. Okay. Remember, because our u is x times y, the x of x encapsulates every single occurrence of an x in our final form. What that means is we know that x of 0 must be 0. Okay. I hope that makes sense. It is a little confusing here. We know that x of 0 must be 0, because for any y we put in, we could put any y into this equation, and when we do this product of this thing and this thing, we know the result has to be 0. So when we plug in 0 for x, we know this has to be 0, which means you can see it already. C1 equals 0. Well, that's handy. because what that means now is that we can write our x of x. C1 is 0, so now we just get C. This should have been a C2 the whole time. I'm being a little sloppy today. I'm just trying to see if you're paying attention. So now we get C2, but now we don't have a 1 and a 2, so we might as well just leave it as C times sine of root sigma x. Well, that makes things a little simpler, doesn't it? We don't even have to worry about the cosine term. We showed that that coefficient is 0, so it must not have a cosine component. So great, so let's apply our other boundary condition. Our other boundary condition is, I believe it was when x equals a, which by the same logic, we can plug it in here when x equals a. We know this happens to equal 0 as well. That's coming from the second part here. Okay. Now, we can ask ourselves, when does this equal 0? Well, sine equals 0 when the argument is 0. Remember, when I say argument, I mean what's inside the function. So if you're in computer science, you're probably like all over that. But otherwise, if you're a silly math boy like me, or any gender expression, then you will be potentially less familiar with that. But regardless, what we know is that what we can say then is that sigma a has to equal. It could be 0, but it also equals 0 at pi. So watch what I'm going to do. So let's just say, so it equals 0 at pi. Cool. But, like I said, it equals 0 at 0. It equals 0 at 2 pi. It equals 0 at 3 pi. It equals 0 at 4 pi, 5 pi, 6 pi, negative 25 pi. You can see what I'm doing. So what we do, and this is maybe the fourth difficult thing about this elaborate process that 309 asks you to do, is you throw an n in front here. Now that we've thrown an n in front of there, we need to make sure, so this is a variable, remember, so it could change. So we said we put a sub n, so give me an n, there, we'll have some sigma that's specific to that n, and then we'll put that n in front of the pi, and we know that this will still be 0. Now, if this feels funny, take a moment, sit with it. It will make sense maybe a little bit later why we're putting n's in the subscript of everything all of a sudden. But let's just run with it for now. So remember, we're trying to solve for sigma, so we know that we can just do some algebra here. Root sigma n equals n pi over a, which means that sigma n is equal to n pi over a squared. Okay? So we've actually done it. We know what sigma is, but what we know is that for a given n, we know what sigma is, right? And so, but potentially n could be anything. If you want to get real fancy, you could say n is in the set of integers, which is written like that if you can't write very well like me. So we can pick any integer we want for n, and this will hold. This will hold. But it will obviously give us a different sigma. Like if this is 0, then sigma equals 0. If this is 1, then sigma equals pi squared over a squared, right? 2, 4 pi squared over a squared. You can see where this is going. So we get different sigmas, but they're all solutions to this right here. They all work. So that's really cool. So what that means is we know x. Sometimes people write a little subscript here. X of x is equal to, remember our constant might change as well now, depending on what n is equal to the sine of root sigma n a, sorry, I'm missing an x here, I believe. Or no, I'm not missing an x. This should be an x. There you go. But remember, root sigma n is going to be the square root of this. So this ends up being n pi x over a. Now, if this is looking familiar, good, because we're going to use that familiarity later on in this example. But for now, we'll stick to it. So great. So we've got our x basically sorted out. Now we need to contend with the y. Now we are going to use one of the boundary conditions of y, but remember y has this weird boundary condition where at the end of or at the end of the interval when y equals b, we're left with this function g of x. So we're gonna worry about that later. But for now, let's just focus on when y equals 0. That's this condition here. We know it equals 0. So by the same logic as before, if we take y of 0, we know this equals c1. If we plug a 0 in for y here, that just becomes 1. Same story over here. So we know c1 plus c2 equals 0. Which means c2 equals negative c1. Which means y can be written as c1, but again, now we don't need to worry about, there's only one variable now. So we're just going to say c times the quantity of e to the root sigma y minus e to the negative root sigma y. Or I wrote root y here, sorry. Root sigma y. Okay, we took a few jumps there. But here's another huge jump we're going to take. This right here is the definition of hyperbolic sine, which, you know, if you didn't know that, what's wrong with you? No, I'm just kidding. That is, I think, one of the absurd things that when I was going through this process for the first time, my professor super glossed over. It's not a huge deal. You could leave it like this if you want. There's nothing wrong with that. But this is a lot harder to write than this. And they mean the same thing. So typically we write it this way. If I would encourage you to look up hyperbolic sine and what it's defined as, and that'll give you a better idea of what's going on here. So here I'm going to pause the recording briefly. Okay, I'm glad I paused and looked this up because I smelled something fishy going on here, but I figured out what it was. The definition of hyperbolic sine is not what I just told you. The definition of hyperbolic sine is this. It's very close. It's e to the x minus e to the negative x over 2. Okay? Now, why doesn't this matter? I'm going to argue that it doesn't matter. Well, basically, what this means is we've got a 1/2 sitting around. So we just bring the 1/2 out, multiply it into the constant, and it's still just some arbitrary constant. So, or actually, what we're doing in practice is we're taking a 1/2 out of this, multiplying it in, and then we're saying, okay, well, that's c times the sine, the hyperbolic sine. Some people call this sinh as well. You might hear that. I don't really like sinh because I think it just sounds silly. So I say hyperbolic sine, so I sound really smart. But for the less insecure of you, you can call it sinh. So here's what's going on. So right. So how would you phrase it? You basically take a 1/2, factor it out of whatever is sitting out in front, slap it in there, and then you've got your definition of hyperbolic sine. You can bring it down like that. So I just wanted to clear that up, but I hope that makes sense. Anyway, cool. So again, we used our boundary condition to develop this. We already know what root sigma is. Remember, it's just this guy here. So now we've got our y of y is equal to c times. But now again, whoa, we're doing sequences potentially. So we need to let it vary given an n. So you give us an integer n, and we'll let it vary. So almost everything is the same. This is mostly a formality. But I do want to be clear about what we're doing here. You get something that looks like that. Okay, cool. So, oh my gosh, like it looks like we've got an x, we've got a y. We're so close to done. I don't know how long this video is, but however long it is at this point, we've made it this far, so we might as well take it home. So we've also got there's a fifth big scary thing that we need to do at the end, but it's honestly probably the easiest out of all of them. So if we multiply these together, here's what we're going to get, right? Because we know that remember this, it's now a sequence, or rather, we need to feed it an n to know what we're talking about here. Equals we're going to bring the constant out in front, and then we just do the sine of, we're just copy pasting now. The sine of all that times the hyperbolic sine of basically the same thing. And there you go. So this is basically the general solution. But we are, well, it's not the general solution, I guess. This is a specific solution. For a given n, it's a specific solution. What we want is the general solution. So there's two more things we have to deal with. One, you might be asking, what is the C of n, or C sub n? And that's a great question. We're going to get there. The next thing, like I just said, is this is one solution for a given n, but we want basically a combination, a linear combination of all the solutions. So what that means is we want to sum over every possible n. So what we do is we let n be positive, and then we just say so what I'm doing here, remember, is I'm summing over all of the n's. All of the n's. But what's nice about this is we can say this honest to goodness equals our general solution, which is what we wanted, right? Honest to goodness equals our general solution. So, great. But again, that still leaves the question, what is the C sub n doing here? You might also be wondering why we start this at 1. But remember, if we plug in n equals 0, we get sine of sine of 0, which zeroes out the whole thing. So you just get 0 plus this sum anyway. So that's why we started at 1. If these were cosines, which I believe happens depending on where, remember I said depending on the side that your function starts on, you get different answers. I think if it starts on, I don't know, one of the other sides gives you cosines and hyperbolic cosines, which people pronounce cosh, because you write it like this, which, you know, this one is much more understandable to me. Anyway, but yeah, so this is our general solution. Now all we need is our C sub n. So this is where things get a little wild, but we need to employ our final boundary solution. Now remember, our final boundary condition was that u of x comma b equal g of x, right? Equal g of x, where g of x is some function. Remember, this is kind of a general, sort of a weird way of phrasing it. This is a general, what we're doing right now is a generalization of a specific problem, if that makes sense. So a problem type that looks like that, like on an exam, what you might get instead of g of x here is this g of x might equal like x squared. But you could see how you would basically, most of this didn't even matter what the g of x was. It only is going to matter in this last tiny little bit. Okay. So what we get here is, yeah, so we have this. Remember, our u of xb is just going to be this with a b plugged in everywhere we see a y. So we know that g of x is equal to, that's not a sigma. C sub n, okay, there's no y's in there, so we're going to leave it as is. Oh, there is a y in there, though, so we get hyperbolic sine of n pi b over a. Okay, now I'm going to rewrite this slightly. I'm only going to change the ordering here. Okay. So look what we've got here. This is interesting. We've got a sine function with an x in it. Okay. So this one is varying. But let's look at our hyperbolic sine function. There's no variables in that. Now, what there is an index. We've got an n sitting there, and we're summing over all n's. So we do have to pay attention to that. But basically, all I'm saying is, given an n, remember, given an n, that's a constant, and given an n, this is now also a constant, because a and b are constants, and n will always be a constant. So what that means is we've got some constant here multiplied times a sine function, and we know that if you take an infinite sum of that, that equals g of x. Now, why am I grinning? Well, that's a definition of a Fourier series, a sine Fourier series, right? So we don't have any cosine components in this one. That's okay. We don't always have cosine components. So that's kind of cool, right? What that means is we know what this constant is. We can use the definition that we have from Fourier analysis. So what that ends up looking like, and I admit I'm looking off to the side here because it is a little hard to remember off the top of my head. But remember, normally it would just be a c sub n, but our Fourier coefficient also includes this hyperbolic sine function. So what we know is that c sub n times hyperbolic sine of n pi b over a is equal to 2 over a. A in this case is our L, if that helps, of g of x times sine of n pi x over a dx. This n is not my best n I've ever drawn. There we go. And this precisely comes, like I said, from the definition of a Fourier series. The crucial piece here, this is the fifth hardest, the fifth hard thing that I was telling you about. We've got a g of x is equal to some basically infinite sum of sine functions with some coefficient, which basically you're supposed to realize, oh, that's a Fourier series. I know what a coefficient for a Fourier series looks like. It looks like this that we've got sitting here. And basically, therefore, you're done. So knowing that this is kind of the case, basically all you do is this. So this is, it might not look like it, but this is your final answer, more or less. Some professors will allow you to leave it in this form. Some want you to solve for c sub n and plug it in. But this is it. So remember, the g of x comes in here. So if this was x squared, you'd put that in. If it were something else, you'd put that in. Normally, it's going to be it might be just a constant or something like that, because as you can see, this integral can get messy if it gets too complicated. So, but okay, that was a lot we went over. I'm hoping the fact that this is pre-recorded means that if you're watching this, you can stop, you can think about it, you can go back, you can read a little bit and come back to it, skip around. But this is basically the technique of variation of parameters. And on the document that this is attached to, I have an example of what a wave equation looks like. I have an example of what oh gosh, what are the other ones? The heat equation. The heat equation is like the most important one. How can I forget that? There's a Laplace equation, but instead of going over a rectangle, it goes over an annulus, which is like kind of like a weird donut looking thing. So there's a couple different ones that we study here at the University of Washington. Yeah, but basically the idea is you can use a technique similar to this for all of them. If you don't have second derivatives, then your characteristic polynomial might have first derivatives kicking around, and you can solve it that way. But the crucial part is kind of this thing here, calling this relationship sigma, and then solving these system of single variable ODEs instead of trying to contend with this crazy multivariable partial differential equation that you've got going on. So anyway, I'm going to leave it there. And yeah, thanks so much for watching. It's been real.